Afternoon, everyone, and welcome to this online seminar from the University of Manchester Institute for Data Science and Artificial Intelligence. I am Alessandro Abate, Senior Lecturer at the Department of Electrical and Electronic Engineering, the University of Manchester, and it is my great pleasure to introduce you the speaker, Professor Alessandro Abate. Alessandro is Professor of Verification and Control in the Department of Computer Science at the University of Oxford. Earlier, he did research at Stanford University and at SRAI International, and he was an assistant professor at the Delft Center for Systems and Control, TU Delft, the Netherlands. He received a laureate degree from the University of Padova and a master PhD degrees at UC Berkeley. Alessandro's research interests lie on the analysis, verification, and optimal control of heterogeneous and complex dynamical models, in particular of stochastic hybrid systems and in their applications in cyber-physical systems, particularly involving energy networks, and in the life science system biology. He is interested in a principled integration of model-based mathematical techniques with data-driven learning algorithms. The title of his talk is Certified Learning or Learning for Verification. And please, Alessandro, the floor is yours. Thank you very much.
Thanks, Alessandra, and good afternoon, everyone. Thank you for having me virtually at Manchester. It's a pleasure getting to know about this institute and about this seminar and contribute to it. So in view of the breadth of this seminar series, I'd like to qualify a little bit what I'm going to talk about today, and also the perspective I'm going to take on data science. So I do research in control theory and formal methods, and I'm interested in integrating data, in particular machine learning, and some aspects of machine learning, we'll see it throughout the talk, in either providing certification to learning components or using learning for verification or control tasks. And that's what I'm gonna talk about today. So you'll see lots of formal methods, a little bit of control, and hopefully some principal use of data. If you have any questions throughout the talk, feel free to interrupt me, although I understand that you may want to as well leave your questions on the chat, and I'll be happy to take them at the end of my contribution. All right, so let me get started, framing a bit more quantitatively my contributions. So this is a seminar about formal methods, which is an area of the computer sciences that has had fundamental impact in many industrial applications. Particularly to prove the correctness of protocols, of analog or digital hardware circuits, and then to find bugs and fixing bugs in software. This is by and large done by developing models of such systems, usually in the form of finite state machines, labeled transition systems, critical structures, timed automata, then encoding what is a correct behavior for such systems, which is done usually through temporal logics or finite state machines, and then developing algorithms and tools that provide certificates, which are mathematical proofs that are automatically generated on whether or not the model of the system verifies the encoding of the property of correctness. So formal methods is about reasoning based on models around the properties of interest. But models, we know, are abstract representations of underlying physical systems. And physical systems encompass data. Data, to me, and in this talk, is conceived as time series of inputs and outputs. Inputs is what you can actuate on your system, how and make it change. And output is what you can sense from your underlying data generating system. So thanks to recent trends underpinned by advances in sensing, networking, embedded computations, the availability of data is becoming more and more prominent. And in particular, there's more sensors embedded in the environment. they crunch more data, and it costs less to do so, right? So if we think of complex engineering system nowadays, beyond the standard successful industrial application of formal methods, particularly in the context of safety critical autonomy, think of autonomously driving cars, autonomous production lines, surgical assisted robotics, and then beyond the sheer complexity of these complex systems, a fundamental question is how to integrate the presence of data in model-based proofs, in particular, given the fact that these systems sense data, modify their models through data, learn the models through data, and therefore we need to make these model-based proofs adaptive, if you will, to the data that is sensed from the system. So in my research and in today's presentation, I'll talk about how to integrate learning from data within model-based verification and control, and this is what I call learning for verification and control, or how to use verification, formal methods, to certify some machine learning schemes. And in particular, today I'll be focusing on reinforcement learning, which is a widely used machine learning scheme to synthesize policies. And this is what I refer to as certified learning. So these are the two different perspectives of how to integrate data with model-based techniques. So here's how my presentation will structure. I'll talk about 4 projects, 2 pertaining to learning for verification and control, and 2 dealing with certified learning. So if there's no questions, I'll start with the first of the 4 projects, which deals with learning for adaptivity and uncertainty quantification. So allow me to go back to the portrayal that I gave before of the relationship between a system that generates data and a model that represents it. We're interested in properties, think of safety properties or properties that we might want the system to abide. And by and large, formal methods is about taking a model and a property and verifying whether the model satisfies that property. And this is done in a number of beautiful automated ways, in particular through model checking, which you can think of as a suite of algorithms and tools that indeed take a model, encoding of a property, and tells you, yes, the model does verify the property, or no, this is a counterexample, this is a bug that you can use to fix your model, and then to fix your underlying system, of course, in a design phase. What are properties? Well, I refer to properties as temporal properties that are rich properties that you can express through temporal logics like LTL, linear temporal logic. So here's the syntax of LTL. And I'm not going to go into the details of it. The takeaway point is that you can express rich, interesting properties, such as something happens at the next step, which is this next phi being a requirement, right? Or maybe a characteristic on the state space of your model, right? Or perhaps something, namely phi 2, eventually happens while phi 1 holds, right? So this is also known as constrained reachability. Or bounded until property. Something eventually happens, or something always happens, right? So these are the properties that I'll be dealing with. These are very rich properties that are used to specify requirement, tasks, goals, right? Or dually to maybe check whether a system has a bug, right? So this is a lack of safety, say, right? So in general, formal methods is about dealing with models and properties. And now, what if we have data? By and large, the classical approach is to update models as data comes in, right? And in fact, to fit a model to data. The problem with this standard approach in engineering and in the life sciences as well is that if the model changes, you need to adapt your proof. You need to maybe restart your proof. And if you want to unfold your approaches in a sort of real-time framework, this may take a lot of costs, computational costs in particular. So I want to move beyond updating models or single models, sort of nominal models according to data. I want to reason more generally at how to integrate data-based learning in model-based verification. And this is what I'm going to discuss in the next slide. So here's a portrayal of how we think of this approach. So here we split model-based approaches in the left-hand side of the slide, where we have the property and the models. And here I don't talk about a model, but I talk about a model class. A model class is a library of possible models. Whatever I can encompass about the underlying system with a priori knowledge, right? Since we deal with engineering system, black box techniques perhaps aren't the best approach. We as engineers have an a priori knowledge of what the underlying system is. Let's encompass this model within a library of this knowledge within a library of possible models, what they call model class. These models, as I'll be discussing later, usually come in the form of parameterized dynamical models. Data is dealt with on the right-hand side of the
Okay. Yeah, it seems that Alessandro got disconnected. I hope he will be able to connect again. Sorry about that.
Hi, I think I'm back.
Oh yes, great.
I hope you guys can still hear me. My fault,
Yes.
My bad. I think my Ethernet crashed. And now I have
that happens.
Both the Ethernet and the wireless connected, and hopefully you'll be able to get a hold of me again. Let me share my screen.
Thank
again.
you. Great. Yes.
If you could give me a second, I have the presentation here with me. Can you see my slides? Yeah? Great, thank you. So again, apologies, let me restart. So here I want to start describing this integration of model-based techniques with data-based techniques. I'll start with model-based techniques, which is here in the left hand of the slides. So here I want to work with a model class and a property that encodes a particular specification. So remember, I don't want to identify, to select a specific model, but I want to work over the whole model class. So what I'm going to do is I will classify the class of models amongst those that verify a property and those that don't. So think of having, for example, some parameterized models. The parameters here are theta. In particular, capital theta is the set of parameters. You can think of this as a model class. And I'm going to carve out within this model class the subset of models that verify the given property. Okay? So this can be done in a number of ways, automated or perhaps based on simulations. And these approaches, this alignment between property and models leverages what depends actually on the kind of model class I'm dealing with, or perhaps it depends on the kind of property that I'm interested in, right? So this can be done. I'll give you some examples of this classification later on in my presentation. Great. So the idea here is that I've aligned the specification with the models. In other words, I want to think about those models that are relevant for the specification of interest. Developing models without knowing how we're going to use them isn't perhaps the wisest thing to do in the context of the applications I'm dealing with. Great. Now, let's comprise the part that deals with data. So again, data are time series of sensor inputs. and I want to update my knowledge on what are good models. Again, I don't want to select just a single model. I want to update what are good models within the model class. And this can be done through Bayesian inference. Bayesian inference starts from prior assumptions of what are good models. Whether these are informative priors or not depends on the applications of interest, and through a likelihood function that depends on the model class, so the structure of your models, updates a posterior distribution that tells you what are the more likely model, given the data you've collected so far. So there's nothing new here. I'm just leveraging Bayesian inference in the context of the models that I'm dealing with. Great. Now, how do I integrate this updated knowledge about the model class with the classification step that I described before? Well, that's easy. And integration actually is mathematically so. So I take the classified model class. Let me project it here on the horizontal axis. I consider the posterior distribution that comes from Bayesian inference, and I marginalize the posterior distribution over the set of classified models. So I take the integral of the posterior distribution over the subset of models that are classified as those that verify the property. And out of this integral, out of this integration, literally, comes the probability that the system that has generated the data, insofar as the data that I've collected, satisfies the property. This probability is a quantity between 0 and 1, and it's something that is a certificate on whether the data generating system satisfies the property rather than whether the models that I'm using satisfy the property. So I've integrated model-based techniques with data-based inference, in fact. So this quantity, this probability on whether or not the system verifies the property is very interesting. And some of you may say, well, can't you not estimate this probability directly from data without using models? For example, doing some statistical model checking or doing hypothesis testing, right? So we've compared our model-based approach against statistical model-free alternative. And of course, as intuitive, as reasonable, we can show that we can converge to the true probability, whether or not the model satisfies the property, much faster than statistical alternative. So the sample complexity is much lower, of course. Evidently, we spend time doing classification, doing model-based techniques, but this is something that you can push offline, right? As new data comes in, this is a very robust property, a very robust quantity, because you can update your Bayesian inference through new data, and your probability on whether or not the system verifies the property gets updated as data may change, may vary with time, right? So this approach can extract more information from the data more efficiently and shows elements of robustness to time variation. And it can be used also, for example, if the system doesn't verify the property or ends up, as it changes with time, to not verify the property, to repair or update the models or the underlying system. So repair of the underlying models can be done by updating models. Repair of the underlying system needs to be done in a way that acts on the system. So acting on the system means controlling the system. And so here we bring back the inputs that I haven't discussed so far, which is what comes from the left-hand side of this block. So inputs is what you can exert on the system to make it behave as desired, or you can use to repair or control the system. So inputs can be, in fact, used not only to control, but also to learn. Let me be more precise here on what we can do with input. Inputs can be used to extract more information from data. This is also known as active learning. So I can push, if you will, the posterior distribution that comes out of Bayesian inference towards a desired region in the parameter space. Alternatively, this is what control engineers do, I can shape, if you will, the set of models that verify the property. I can make more models verify the property. I can repair models, if you will. And of course, the underlying system, if I then apply the input onto the underlying data generating system. So there's this duality between learning and controlling that I can tackle with inputs. So in the next few slides, I'll tell you how to do a little bit of active learning, which is what is in the top of this slide. and so how to extract more information through input from data. So I'm going to go back to the portrayal that I introduced before, and I'm going to update it with a new block that you'll see here. In this central block, we now have strategy synthesis, which is something that we synthesize through models, much like what we do in control theory, but which requires updating models, because when we synthesize an input, when we apply it to the underlying system, we generate new data. New data is used to update the models through Bayesian inference, and hence Bayesian inference needs to be integrated with strategy synthesis. So this is a very interesting problem of exploring and exploiting, of learning and deciding, right? So it's an integration, again, of learning with, well, control synthesis in this case. So this integration can be done in a number of ways, which again depends on the kind of properties we're dealing with, on the class of models we're dealing with. By and large, the way that we do it is with Bayes adaptive approaches. For example, based on Monte Carlo tree search, which exploits simulations from the underlying models. If the models are complex, also Bayesian inference needs to be done approximately. In fact, we leverage approximate Bayesian computation approaches that are based on sequential Monte Carlo algorithms. The very same algorithms that we use also to synthesize strategies, in fact. The sequential Monte Carlo algorithms also underpin how we do model classification through simulations of the models. This is known as statistical model checking in the formal verification communities. So here, again, we generate trajectories from the models to generate policies, inputs, strategies that generate new data that we use to update the models. So here you see, again, the integration of learning and reasoning in the sense of verifying or controlling, right? So we've applied this general approach that I described in a number of different instances with different model classes, say, for example, Markov models, Markov decision processes, continuous time Markov chains for systems biology applications, or linear time invariant models with correspondingly relevant specifications, whether it's in probabilistic branching logics, other kinds of logic like LTL or CSL, and with a number of different approaches to do model classification or Bayesian inference, with applications ranging from energy biology and more standard control engineering. So I hope this description makes sense. If there's questions, I'm happy to take them. Otherwise, I'll move on to the second project, which again deals with learning for verification and control.
I have a quick question.
Yeah, please.
Could you please tell me again why the model-based learning is better compared to statistical learning?
So we need to qualify what we mean with better. And if I use this adverb, I should be more precise. I mean that it's simpler in terms of sample complexity. That is, I need less data to attain the same level of certificates, statistical certificates, that I would otherwise need to attain with statistical approaches. And it's more robust in the sense that if data varies, I can get updates that are model-based, and I can predict how these variants will unfold in time. And I can use it, I can use models to do active learning in a way that is model-based and hence perhaps better in the sense that I can extract more information than what I would otherwise be able to do with black box approaches. Does it take your question? Am I convincing?
Yep, thank you, I appreciate it.
Thank you. Great. So if there's no other pressing questions, I'll move on to the second project, which is called Learning for Sound Synthesis. So this is more of a control theory project, if you will. And in fact, let me start with some control models. So here you see a system, a two-dimensional system of ordinary differential equations. It describes the rate of change of variables x1 and x2 as a function of time through a vector field f, which is here a linear vector field, but it could be a more general non-linear vector field, for example, polynomial, as in this second example. If you are from computer science, you can think of these dynamical systems as programs, in which case you'd be working with discrete time versions of these models, perhaps with variables that take values in a lattice rather than in R2, as in this case. So we want to study two fundamental problems for dynamical system. The first is stability, and the second is safety. So let me clarify what I mean with that. Stability is a problem that deals with equilibria of these dynamical systems, which are points that are defined here as xc, where the vector field is equal to 0. That is where the dynamics don't move. Okay, the dynamics are still, if you will. So the right-hand side of these two ODEs is equal to 0. Now, how do we ensure stability of these equilibria? We can do it classically, standard in control theory, with Lyapunov functions. If you are from programming languages, Lyapunov functions are the analog of ranking functions to study termination of software programs. So all I'm saying is that what I'm describing here for dynamical system works also for many classes of software programs. So a Lyapunov function is a function that maps the state space of my dynamics into the non-negative reals, and which satisfies two requirements. The first is that it's non-negative, and the second is that it's Lie derivative, which is the dot product of the gradient of this function times the vector field is negative. So you can think of these two conditions as follows. First of all, the Lyapunov function needs to be nice and sort of quadratic looking, so it's positive. And if I start a trajectory on its surface, then the derivative of the trajectory along the surface needs to decrease. So that entails converging, if you will, towards the equilibrium point, which is what I mean with stability. So if you find a Lyapunov function, this is a certificate that the equilibrium point is stable. Similarly, if you find a ranking function, you know that the program will, say, terminate, for example, right? So there is this analogy between ranking functions and Lyapunov functions. So this is to study stability. We are also interested to study safety. So here the problem is the following. We start from an initial set x0, which is here in green. And we have a set of unsafe states, which is called xu, which is here in red. Here you see a 2- and 3-dimensional representation of a dynamical system. You want to make sure that there's no trajectories that start from the set of initial conditions and enter the set of unsafe states over a domain around these two sets. And you can do that if you can synthesize, so again, a sufficient certificate to do so. You can synthesize a barrier certificate. Very similar to a Lyapunov function, maps the state space into the real numbers and needs to satisfy similar requirements. The first is, there's 3 requirements now. The first is that it's negative over the set of initial conditions. It's positive over the set of unsafe states. And whenever it's 0, we want this function to be continuous. Whenever it's 0, we want the derivative to point towards a set of initial conditions. If we can find one such barrier certificate, then this is a certificate that the system is safe, namely that there's no trajectory that starts from the initial set and enters the set of unsafe states, okay? So the idea is, how do we synthesize these functions in a way that is automated and sound? And we do it with an approach that leverages learning. In particular, this architecture called SEGIS, counterexample guided inductive synthesis. This is an architecture that has been developed in the formal methods and programming language community to synthesize programs through templates, through blueprints, if you will. So the idea is that synthesis is hard per se, but it can be broken down into guessing and testing. Guessing a candidate for the Lyapunov function and testing that it is a valid Lyapunov function. So we break down the synthesis problem into the problem of learning a candidate and then verifying that such candidate actually is one such Lyapunov function or barrier certificate. So we generate these candidates through a learning approach that I'll be describing in the next slide. Then we pass these candidates to a checker, which is a SMT solver. An SMT solver is a tool that generalizes satisfiability theory into theories of nonlinear arithmetics over the reals. And they can validate whether this candidate actually is a proper Lyapunov function, that is, or Bayes certificate, that is, that it does verify formally, soundly, the requirements that I stated in the previous 2 slides. Whenever this holds, then I'm done. I've provided such a synthesis. Whenever this doesn't hold, this verifier produces a counterexample that can be used to generate new data that is used by the learner to provide a new candidate, to do a new guess of what's a good candidate, which is then passed to the verifier that tries to check it, right? Until I provide a valid, sound certificate. Evidently, for complex problems, this loop might not terminate. So there is an issue of completeness, but in practical scenarios, actually this synthesis does work and can be applied in particular to synthesize Lyapunov functions and Bayes certificates. So to give another slide with a few more details, essentially what we do is we take the requirements, say for Lyapunov functions, and we encode them as a second-order logical formula in the theory of real numbers, of no-real arithmetics over real numbers, pass them into a SAT solver that does the check. The candidates are generated either within polynomial functions, or, and this is where learning really comes into play, through neural network templates. Neural networks are maybe simple architectures. They don't need to be very complicated. We don't need to use deep neural architectures, in fact, not at all. They're general approximators of complex functions. And we feed these counterexamples and data on the state space of the models to provide guesses by just training these neural networks with loss functions that actually are proxies over these requirements that I've stated here on the top of the slide, and provide really good candidates that then are passed to the SAT solvers that provides formal proofs that they're actually Lyapunov functions and Bayes certificates. This is a new approach that actually integrates using learning architectures, neural networks, to do synthesis of standard Lyapunov or Bayes certificates, which has been pursued for decades in control theory, in fact. And it works. It works. So doing this training actually is quite promising. So here are examples where we have nonlinear systems. We generate Bayes certificates. This is an example where you have a hybrid system. We generate a Bayes certificates, a separate, again, set of initial sets from set of unsafe states. And here's a Lyapunov function, which is a 4th order polynomial that we generate for the 6th order ODE, ordinary differential equation. And we have a tool called Fossil that is being released as I speak, that can be used to generate these certificates automatically and soundly. Again, the takeaway point is to use learning techniques to solve control or verification problems. Great, this brings me to the end of the first part of my talk, and I see that I have another 10 to 15 minutes, which I'd like to use to describe the second contribution, certified learning, unless there's pressing questions. So I'm going to pause and sip some water. Great, if not, then I'll move on to certified learning. So here the approach is dual. I want to use formal verification techniques to certify learning architectures. And what I'm going to refer to is reinforcement learning architectures. So RL is a widely used architecture in machine learning to synthesize policies, strategies, inputs, actions that maximize a cumulative reward by probing the environment by an agent and measuring local rewards that come from the environment. It has had a number of success stories. And the fundamental question that we're trying to solve is whether we can synthesize policies that are correct by design, namely that abide by requirements, by tasks, in fact, by specifications encoded in temporal logic formula So we want to correct by design certified synthesis of policies around these requirements, goals, or objectives. So we have an architecture that does that, which I'm going to describe in the next few slides, which is called logically constrained reinforcement learning. So the idea is the following in a slide, and then I'll give you some more details. We have a specification, which is an LTL formula, a formula in this temporal logic that I showed you before, which we translate into an automaton. An automaton is a finite state machine that encodes this formula. We synchronize the automaton with the environment. Essentially, we use the automaton to monitor how the agent is exploring the environment. This exploration leads to guided synthesis of policies that we prove maximize the probability of satisfying the LTL formula that we were given. In other words, we prove that asymptotically through standard RL temporal difference algorithms that we'll be describing shortly, we can synthesize policies that maximize the probability that these temporal logic requirements, that these goals are indeed satisfied. So let me give you some more details on how this is done. First of all, let me start with some background, a couple of slides on reinforcement learning, just to get everyone on the same page. So I'll be focusing to begin with on a state space that is an environment that has a finite number of states and a finite number of actions. So think of a grid word, if you will. We use a Q function, and I'm referring to Q learning as a standard temporal difference learning scheme, which maps pairs of states and actions into the real numbers. This Q function is initialized arbitrarily, uniformly, say, and it's updated locally as the agent explores the environment, as the agent visits a particular state S and takes action A. So here's the update rule that I show at the center of the slide. The Q function is updated through the local reward plus the maximum difference between the Q function at the next state, given any possible actions that I can select. There's two parameters here, which are standard parameters, a learning rate mu and a discount factor gamma. Okay, I'll be looking at this Q learning in an episodic fashion. That is, I will reinitialize explorations after a number of steps, but it can be seen also, it can be also looked at in a continuous exploration fashion. And the fundamental question is convergence of this Q function, right? And what is the resulting policy, which is a map between states and actions. I'll be focusing on stationary policies, positional stationary policies, that is deterministic maps between state space and action space. And let me introduce this value function, U, that depends on a given policy pole, as a discounted accrued reward taken in expectation over episodes that an agent experiences. The optimal policy is the policy that maximizes this discounted expected reward. And a standard result in Q learning is that if you let your agent explore all states infinitely often, then you converge to a Q function under some standard assumptions that I don't state here for the sake of simplicity, but these are rather weak and standard assumptions. It converges to a Q function Q star, out of which you can derive, you can distill your policy. And the policy that you can find is the one that maximizes this value function here, right? Namely, it's the policy that maximizes this expected discounted additive reward. Now, this is standard Q learning applied to reward-based feedback. What if we want to synthesize a policy that maximizes the probability of verifying a specification? So here's how we do it. We first consider a specification, again expressed in LTL, linear temporal logic. So I've introduced this syntax of LTL and the semantics of basic formulae earlier. Same thing here. What we do is we alternatively express this LTL formula as an automaton. There's various automata that we can use for this task. We need to select some automata that are relevant for the models that we're using, in particular Markovian models. And in particular, here we use this class of recently introduced automata, which are known as LDBAs, limit deterministic Bucci automata. So a slight modification of well-known Bucci automata. So these are finite state machines that express properties like the following. Eventually, always, something holds. So this is the automaton here on the right-hand side that expresses it. It has an initial state and an accepting state here with the sort of double circles. So accepting states are subset of the state of the automaton that correspond to accepting conditions, that is, traces that are satisfying this property. Here's another formula that says A and next, eventually always A or eventually always B. This is a more complicated formula in LTL. It very much makes sense if you hear it spoken out, right? And on the right-hand side, you see an automaton that expresses it. Now, this is, for those of you that are interested in automata theory, not the standard Bucci automaton because it has this epsilon transition. It's a limit deterministic Bucci automaton. I'm not going to get into the details of it. It's an alternative to Rabin automata, which are relevant for the kind of applications that I'm interested in, probabilistic models, Markovian models. But they're more succinct than Rabin automata, and hence that's why we use LDBAs. What is important about LDBAs are these accepting conditions that characterize good traces, good episodes, good explorations, if you will, in an RL context. Now, if you have a model and an automaton, a standard approach in formal verification is to take the product automaton, that is the synchronization between the model, an MDP, and an automaton that expresses a specification. Here on the right-hand side, you see an automaton that says, that expresses eventually alpha, right? And here's the product MDP that you generate, right? So we don't need to generate the product MDP in our context, which is instead what's usually done in formal methods, because in our context, well, our approaches are model-free. We use reinforcement learning. So we don't know the underlying MDP model of the environment and of the agent, right? We use the automaton to monitor episodes that we take through Q-learning or any temporal difference technique, and see how the agent has progressed to verify the specification of interest. And in fact, we provide rewards to the agent, depending on whether it has satisfied, at least in part, the specification of interest that we're monitoring through the automaton expression. So that's the idea of the reward assignment for logically constrained reinforcement learning. We assign reward to good explorations. Imagine to have an automaton and having reached a part of the automaton that is expressed here. Assume the automaton has two accepting sets, F1, which is state Q1, and F2, which is states Q2 and Q3. If we are at a point in the state space that corresponds to the state Q0 of the automaton, by entering Q1, which is what I do in the next step, I give a positive reward to my agent. And I extract F1 from this set capital A that I use to monitor the exploration of the automaton. At the next step, I'll jump from Q1 to Q2. I'll give a positive reward to the agent because, again, I'll be visiting F2, which I extract from set A, and I reintroduce the F1 set. At the next step, I'll visit Q3, but because I've already visited F2, I will not give the agent a positive reward. I'll give it a neutral reward. But at the next step, by action A, I'll be visiting Q1, so I give the agent a positive reward. So what is the takeaway point of this sort of movie? That I'm rewarding the agent to create episodes that keep on visiting accepting states, which is associated to trajectories that verify the property. So by providing this state-based reward that depends on the monitoring that comes from the automaton, I can use Q-learning architectures or other temporal difference learning architectures and come up with good exploration that synthesize policies that maximize actually the probability of verifying such task, such requirement, such LTL formula that is expressed by the automaton. I hope that this is a bit hands-wavy, I understand, for the sake of time, but I hope it's the takeaway point is clear. And in fact, we can prove that by properly selecting these rewards and also the discount factor under standard assumptions, which are the standard assumption in Q-learning, we can synthesize a policy asymptotically that maximizes the probability of satisfying the typologic requirement, the goal, the task that I gave to my agent, right? So we can do effectively certified correct by design synthesis towards satisfying some goals with machine learning, reinforcement learning algorithms. Some experimental outcomes, just to complete the presentation. Here's a pursuit evasion game. I have an agent on the northwest corner of this grid that ought to get to the 2 food sources here while escaping 2 pursuers, P1 and P2, that randomly move with a drift towards the pursuit evasion, the evading agent. This is what I call with my students Pac-Man for DARPA. If you try to achieve this objective with simple rewards, which is follow the food sources, in particular the closest one will give you more reward, then you won't be able to find a good policy. Why? Well, because given the initial conditions here, you get locked by the 2 pursuers. However, we can express this requirement that I sort of expressed in natural language with a LTL formula, which is this task here, and the corresponding automaton up here. The task says eventually either visit the first food source and then eventually the second, or the second food source and then eventually the first, whilst always avoiding P1 and P2, the 2 pursuers. We use this automaton, provide feedback that depends on the accepting conditions, which is this Q3 state, and we can synthesize policies that are indeed successful. We guide the exploration in a way that is smarter than simple rewards. We can do it also for more complicated games like Montezuma Revenge, something that even DeepMind struggles with. Here you have this agent that needs to first get the key, then open the door while avoiding this school that moves periodically. Complicated task, but it can be coded easily. Eventually gets the key, and eventually the door, and avoid always the skull, and never get to the door without the key. Here's the automaton that expresses this requirement, and we can synthesize successful policies quite easily. Recent work that has appeared last week at AAAI actually extends what I'm talking about in this presentation to the problem of learning the specification, learning the automaton. What if I don't know the specification? What if I have to learn it based on rewards from exploration? More complicated task. So this is something that we call the deep synthesis. We've extended this to infinite state and action spaces. This is through deterministic policy gradient techniques, and in particular, exploiting architecture known as actor-critic reinforcement learning. So there's a critic that gives you feedback on your policy, and an actor that updates policy following a gradient. These regressions over a continuous state and action space is done through basis functions, or in fact, we use deep neural networks to do that. Again, using learning techniques to do strategy synthesis. And this allows to synthesize policies that work on continuous spaces and continuous actions. Here's a Mars rover setup where I have to get to some targets while avoiding falling off a cliff, essentially, or gets to 2 sequential targets, T1 and T2 on the right-hand side while falling off a cliff. So here are my specifications, and the corresponding automata are at the bottom of the slide. And here are successful applications of policies that I've synthesized with DPG, the actor-critic scheme that I introduced before. Here, actually, we have discrete actions. Here we have continuous actions, as well as continuous spaces. And we can deal with complex tasks like these 12 sequential task assignment, whilst keeping safety, that is not falling off the cliff of this Mars rover setup. Here's an OpenAI setup where we try to stabilize an inverted pendulum while avoiding the red regions and while infinitely often visiting the yellow and the green ones. It's a rather complex setup that we can synthesize policies to attain these goals. And this brings me to the end of, well, the first part of this second project. I think I'm running out of time, so I should stop here. Maybe I can take 30 seconds to just provide an idea on what are the current extensions of this line of work, if it's okay. So really, I'm not taking more than 30 seconds. So far, I've synthesized policy that maximize the probability of verifying a goal, a task, a requirement. Say, for example, a safety requirement. I want to synthesize policies that at runtime, when I apply them, will be maximally safe. What if I want to be safe while learning? What if I want to generate episodes that are safe as I learn, not just when I apply at runtime the policy, but as I synthesize the policy? I want to go from ensured learning to assured learning, if you will. So this is something that we're studying right now, and we have a recent study that was published last year at AMAS that does that. It's called cautious reinforcement learning. For the sake of time, I'm not going to present the details of it, but this is a direction of ongoing work. The takeaway point is you cannot do it in a model-free way. You do need a model and update the model in order to encode, to quantify what is the level of safety of your exploration. So it's a more complicated task that needs to be thought about with further integration of model-based and data-driven techniques. And another project that we've been working on is indeed learning not only the policy, but also the specification through exploration. And again, there needs to be a trade-off between exploring and exploiting, between learning, maybe a model, and then using the model to synthesize a policy. I'm skipping the details of these extensions with the hope that I've enticed your attention and you'll be looking at the references that I want to quickly show you at the end of this deck of slides. And whilst I do that, I'd like to thank my students and collaborators, and I'll be happy to take questions. Here are selected references for your perusal. Thanks for your attention.
Thank you very much, Alessandro. I think that is a virtual applause. It was very interesting presentation. And now I think we can open the floor for questions. We still have 5 minutes or so. So you can either write a question down in the chat or turn on your microphone and speak. Okay, maybe I start with I can kick off because actually I work within the power system area. So I think that I started to think of many possible applications of these concepts, especially the formal verification, the safety, and the first part that you, when you describe the sound, like Lyapunov barrier synthesis. So I was thinking that, for example, within the power system, there are many types of different faults that might need to be characterized and also learned. And also it might be possible maybe to use these concepts to try to characterize and learn conditions that might lead to unsafe region or might lead to a fault. Do you see that it's something that could be feasible, doable?
Of course. So fault detection, fault isolation, fault resolution is standard data-based problem that has been studied for discrete event systems in particular, but also for dynamical systems, right? And I think it's relevant also for, I mean, it might be relevant, you know better than me for sure, for power system applications. Now, it hasn't been tackled with modern machine learning approaches, as much as I know, I'm sure that this is not quite true, because I haven't followed the fault detection and resolution literature closely most recently. But I think that it does make sense to try to think of faults or learn faults from data and in the context of power systems. In this context, I've done a little bit of work where I've used models, but not learning, to study arisal of blackouts on power networks. The setup was the following. We built models for the dynamics of photovoltaic panels. These were simple models that had essentially 3 states: off, on, or waiting to be on after a disconnection, right? Then we assumed to have an heterogeneous population of such panels that interacted with simple dynamics of the frequency in time from the power grid. These were dynamics that were provided by a transmission system operator, in fact, the French TSO, RTE. We consider a large-scale models of these heterogeneous population of photovoltaic panels, and how essentially the dynamics of photovoltaic energy production interacted with the dynamics of power and frequency over the grid. We estimated probabilities in the short term, so over sort of primary control timescales, the probability of blackouts, depending on the specifications of the photovoltaic panels over the population. So we had a distribution of, say, for example, disconnect and reconnect frequencies, and time of disconnection and reconnection. There was heterogeneous over the population and described by some distributions. And we got some results that were, well, convincing to our collaborators, but they were purely model-based. And in particular, we used these Markovian models with probability distribution that were given, if you will. Now, natural extension would be to learn these probability distributions by monitoring the photovoltaic panels and updating this probability distribution, maybe in a Bayesian framework, and understand how this update interacts with the proofs that we're able to generate based on the models of the dynamics of the frequency interconnected in a closed loop with the simpler sort of 3-state dynamics of these population of photovoltaic panels.
Okay, that's very interesting. Thanks. Any questions? Okay, I think that now it's 3 o'clock, and I think that we can close the session, and maybe, Alessandro, we can discuss more about that offline.
Absolutely. I'd like to apologize for the disconnection, but I'm happy that I survived
no
the Ethernet crashing. And I'd like to thank you all for your attention, for showing up today. And should you have any questions, here's a website of my group, and feel free to contact me.
Actually, Alessandro, can you please flip back to the pages for references?
Yes, absolutely.
Because, yeah, thanks.
I did cover all of these pages, so if you browse back on the video, you'll see them. But here are the references. This is to own work, and then this is related work. And I'm happy to share the slides just in case.
Okay, great. Thank you very much again. Thank you very much, Alessandro, and all of you for attending. And well, I wish you a good evening.
Thank you very much. Good to see you.
Thank you.